My name is Sal Lázaro and I'm working on chapter 14, number 19. The problem says a playground is on the roof of a city school, 6 meters above the street below. The vertical wall of the building is 7 meters high, forming a 1 meter high railing around the playground. A ball has fallen to the street below and a passenger returns it by launching it at an angle of 53 degrees above a horizontal at a point 24 meters from the base of the building, which would be from here. The base of the building is here, and the wall goes up to 7 meters here, and the playground ground is 6 meters high. Okay, so the ball takes 2.2 seconds to reach a point vertically above the wall. So this point right here, that point right there. Alright, so now what we're going to do for part A is we're going to find the speed at which the ball was launched. So this velocity right here is what we're looking for. Alright, so here are our knowns. We know that our data is equals 53 degrees. We know that for x, we have data x equals 24 meters. So from here to here is 24 meters. Our acceleration at the x is 0 since it's free fall right here, 0. And our velocity initial is cosine of theta, which equals to our final velocity. Since it's a free fall problem, there's no acceleration, therefore our velocity is not going to change at the end. It's going to be constant all throughout. Our time would be 2.2 seconds, and now our knowns for our y, our data x, we don't know, which is from here to here. That we don't know, which we'll find later. And our acceleration is negative g, so it'll be, since it's being pulled by gravity, is negative g. And then our velocity initial would be this, which is v initial sine of theta right here. And this number, I'll show you how I got it in a little bit. Alright, and our velocity final, we don't know, because we don't know at what point we're going to stop. So to find the velocity at which it was launched, we're going to use our knowns for our x. So we have theta x equals velocity initial times time plus 1/2 acceleration times time squared. But since our acceleration is 0, this whole thing equals 0, giving us theta x equals velocity initial times time. Then we solve for velocity initial, which is theta x over time, but our velocity initial right here, we know that is this velocity times cosine of theta. So we plug that in and we divide by cosine of theta as well. So our velocity initial, once we plug in the variables, we could see that it gives us our velocity from what it was launched, which would be 18.13 meters per second. And once we have that velocity, we could find B, which is find the vertical distance by which the ball cleared the wall. And that would be, since we found our velocity, we plug it in right here. That gives us 18.13. And right here we have data x. Our kinematic equation is data x equals velocity initial times time plus 1/2 acceleration times time squared. But we know that our acceleration is negative gravity, so we plug that in. and then we work it out. Delta x, all this, we plug everything in. So our velocity that we got from part 1 right here is 18.13. So we plug that in and we multiply it times sine of 53, which is our velocity right here, our initial velocity in the y, times time minus 1/2 gravity, times 2.2 squared, which would give us this. But this is not our answer, since this is the distance above the level ground right here. So what we do, since this is our distance above the level ground, and what we're trying to find is the distance from here to here. So the distance from here to here, we know that this is 7 meters, and we found this, so we will subtract that. Oh, there we go. So our answer minus 7, which would give us the answer that is 1.133 meters. Now we work on part C. Find the distance above the wall to the point of the roof where the ball lands. So for this part, since at 2.2 seconds the ball was right here, our y, we know that our y has to be 6 since it's going to land on the roof, but we know that it's going to take longer than 2.2 seconds. So what we're going to have to do is we're going to have to solve for our t, and our t is greater than 2.2 since we know that. Alright, so we know that our y is going to be 6, and we plug that in. We set our kinematic equation. We know that our acceleration is negative gravity, and we will leave it as a just to solve the problem. We'll plug in it later. And we set it to 6 equals velocity sine of theta times time plus 1/2 negative gravity acceleration plus time squared, and then we set it to a formula so equal to 0, so we could use a quadratic equation, which is this right here. So now what happens is that once we have, so this will be our A, this will be our V, and this will be our C. And we plug them in. So so it's negative B plus or minus square root of B squared minus 4AC. Or 2A, we plug them in. And then you see that since A is A over 2, okay, since A right here is A over 2, A, B, and C. Sorry, A is A over 2. The 4 and the 2 cancel out, giving us 2, and the 2 multiplies to 6. So once you work that out, and you do some more cancellation right here, you'll end up with t minus sine of theta plus or minus the square root of this. We keep on solving it till we get the numbers, and we get t equals this. So then we work it out minus and then plus, and then we add right here and we subtract right here, thereby getting t 0.456 and 0.49, but this one right here isn't greater than 2.2, so this one gets canceled out. Then we plug it into our kinematic equation for x to find it, but that will not give us the whole thing. What that would give us is from here to here, and we don't want that, we want this distance, so we have to subtract 24. And the reason why it is 24 is because this. Alright, And once we have that, our answer 26, we subtract 24, and our answer is 12.79.